Yes. All right. Yeah. Thank you, Leo. Yeah, I'm very happy to talk today. So I'm going to avoid saying that I'm super disappointed not to be in Buenos Aires, but we all share the same feeling. Yeah, so I'm going to talk about two research works that we've done with Cecile Maillet, who is also in Bath, and Bruno Schapira in Marseille, about a procedure of reinforcement learning whose purpose is to find, hopefully to find the shortest paths from a point A to a point B, or N to F, as I will call them later. And the starting point of that problem is the following. So the real starting point actually is that in almost every paper about reinforcement homework, so you have this sentence in the introduction that says, oh, reinforcement homeworks are actually used to model how ants find the shortest path from their nest to a source of food, right? And actually, mathematically, there's not a lot of models and of results trying to explain that, right? So the goal of our works is to try to find what's the right model to explain this behavior, this phenomenon, and try to study it as much as we can, right? So that's the starting point. This phenomenon, according to which the ants can find the shortest path from their nest and to a source of food F, right? And there are other similar phenomena, something called physarum, which is like a kind of fancy mushroom that grows a network that connects different sources of food using like some kind of optimal transport network. Okay, and that's the same kind of model that apparently use a dynamic involving reinforcement, right? So the reinforcement for the ants would be produced by the fact that they leave pheromone behind them, so that the next ants will be more likely to go through the same path, right? Because they will smell or feel the pheromone, right? And there are quite a few of work in biology about it, okay? But that's work in biology, so it's not really studied mathematically, and the models that they use are both deterministic and Millfield, right? So deterministic meaning, but at the end it means that they look at differential equations, right? Deterministic differential equation, and they try to see that these equations work like they want, right? So what we wanted to do is to take a different point of view because we're probabilists. So we wanted to define a model that is probabilistic and that is local, right? Where the interaction is local or agent-based, right? And I did here low level of rationality because, okay, we want to explain how ants find shortest path, so you're not allowed to say, oh, just open the map and look where's the shortest path, right? So you want a notion of low rationality there, right? Or that's related to the fact that the interaction is local, right? So there is these two good sentences that encapsulate what we want to do. So the first one is told it to Pierre Tarès. So global learning from local interaction, that's exactly what we want to do. We want to see a local interaction of the ends of the random walks and see some kind of global structure emerging from there, right? And another fancy word that could correspond to that is self-organization. All right, and as I just said, the basic idea is to use both random walks and reinforcement in some way. All right, so I'm going to explain now what's the model that we defined, and later I will tell you how we think, what we think happens, and then I will tell you what we proved happened. Right, so there is a lot of open questions left, but we have some results. All right, so what's the basic model? So the basic model, you take a finite graph, okay, and you distinguish two vertices, the nest N and the food F, right? So that's your graph G with vertex set V, edge set E, right? And to initiate the process, you just assign to each edge of the graph, each edge E, you assign weight 1, all right? And what we'll do then is that we're going to play a game having infinitely many rounds, and after each round, we're going to update the weight of these edges. Okay, I'm going to tell you how. All right, so we start with weight 1 everywhere. Assume you've built your process up to time n. What do you do at round? When I say time, I think round, okay, because there will be random walks and it's not the same time. So let's say round n plus 1. well, you're going to send an ant from N to F. So what this ant is going to do is just a random walk. Okay, it's going to walk around the stuff up until the time it hits F. All right, and then you stop the random walk. Okay, and the ant is not going to walk just on the graph; it's going to walk on the network GWN. Right. So what it means that you have these weights WN of E on each edge, and this gives you conductances for the edges, right? And what the ant is going to do is to do a random walk on this network with the weights Wn, right? So for example, here I just tell you the probability to jump through an edge E3 here is going to be proportional to the number to this number Wn of E3, right? This weight at time n for the edge E3. I didn't tell you what it corresponds to yet, but I'm going to tell you. Okay, there are different possibilities. All right, so you have this ant that has done something, you have the trace of this ant, and then you're going to look at this trace. Okay, that's there, that's the trace. Okay, and according to this trace and according to some reinforcement rule, you're going to update your weight from Wn to Wn plus 1, okay, for each edge. Okay, so I didn't say it was a reinforcement rule. I'm going to tell you what you can choose. Okay, so so far I just tell you it depends on what the ant has done. Okay, and there are different possible choices for this reinforcement rule. Okay, so the basic stuff. So I'm going to go ahead of the next slide because I have the picture. I don't remember if I have the picture in the next one. The basic stuff is that we're going to reinforce a subset of this trace, right? And you have different sensible choices. I'm going to explain what are the differences and why they are all good choices in some way. All right. So what are the possible reinforcement rules? So what I'm saying here is that, okay, you have the trace of your nth ant. You're going to choose a path gamma n, okay, which is a subset of the trace. Okay, so all the edges of gamma n are edges of the trace, all right? And this path starts from the nest and ends up at the foot. All right, so it's a subset of the trace that goes from N to F. All right, and once you have chosen this gamma N, you just add weight 1 to the edges of gamma N, and the other edges, you don't change them. They stay as they are for round N plus 2. All right, okay, so you just update, you put plus 1 to the edges of gamma N. Okay, so now how do you choose gamma N? All right. Well, I'm going to give you 3 possible rules. I'm going to tell you what are morally the differences. Okay, so the first rule you could think of is the following. So you that's what we call the uniform geodesic end process. So here assume that your ant has walked, leaving a trace that looks like that. Okay, so it does work like that. And then you're going to say, okay, the ant is going to lay pheromone on its way back to the food, to the nest, sorry. And the ant is an expert level hiker. So it remembers where it went, or it can feel where it went, but not only that, it can find the shortest path already coming back to the nest. Okay, so the ant is going to choose a geodesic of its trace, right? A geodesic of its trace. And if there are several geodesics, then just chooses one at random with equal probability. All right, so hence uniform geodesic. Okay, you reinforce one of the geodesics of your trace. Okay, so okay, that's one possibility. So that would be for ants laying pheromone on the way back, which is the biologist consider all these different cases, right? If the ants lay down pheromone on the way forward, on the way back, or both, with different level of rationality. So here it's a pretty high level of rationality because the ant can find the shortest path just remembering a whole trace, right? So it's a pretty high level of rationality. Another possibility, it's actually my favorite one. It's called the loop erased, or what we call the loop erased end process. So here's something. I assume that the ant has walked that trajectory here. Okay, and what you're going to do? Well, you're going to go back from N to F. Actually, the way that I think a real life hiker or most people would go back to their starting point, which is every time I'm somewhere, I'm going to go back through the edge I first came from. All right. So every time you end up in a place, when you go back, you just take the edge that led you the first time to that place. Okay. So on this picture, it's this path here, okay, which is different from the geodesic, which is that path. Okay, so you're not going to reinforce a geodesic of your trace, you're just going to reinforce a loop erasure of your backward trajectory. Okay, so you walk backward, but you don't do the useless loops. All right, so that's a hiker with local memory. He just remembers where he first came from, right? And again, yeah, mathematically is the loop erasure of the backward trajectory. Okay, so that's also something actually that was considered in the biology literature. And the last one I'm going to discuss is just the one where you reinforce everywhere you go, right? So here the ants just leaves pheromone as it goes towards the food. All right, so it's laying down pheromone on the way to the food. All right, so that's the trace reinforcement process. You just reinforce the whole trace. All right, so as you can see, so that's three small variation or variation that could seem small of the same model. But as I'm going to explain, there are some differences between this model, in particular with the trace reinforcement network. So the question for us was, well, which model works and which model doesn't work, in the sense, which model allows you to find the shortest path from N to F, right? Without losing time, where the ends don't lose too much time, right? So don't go through longer ways for too long. All right. So here are the conjectures. Okay, so the first conjecture is that you take any finite graph with these two vertices N and F. Then if you normalize the weights after round N by N, this should converge homosurely, all right? Okay, for any of these three variations. And now I'm going to distinguish between the three variations. So the first one for the, actually it was the second one, the loop erased N process. So essentially we think that this model allows you to find all the geodesics in a graph, right? In the sense that an edge is going to survive if and only if it's on a geodesic from N to F. So depending on the structure of your graph, this could be meaningful or not. But if your graph is nice in some way, then it just means that the ends eventually will travel along geodesics. All right. For the uniform geodesic end process, well, we think that if an edge survives, then it can only be along a geodesic. So if it survives, then it can only be along a geodesic. Okay, so the difference with the first one is that it does not find all the geodesics. Okay, some of them will die out. Die out in the sense that this proportion will go to zero, right? So asymptotically, zero ends in proportion will go through other paths. And did I do? Yeah, for the third one, for the trace reinforce, well, it's actually not so clear what's happening in general, but what we know for sure is that this process is suboptimal in the sense that some edges that are not along geodesics can survive, and even dead ends, right? So your ends can just keep on going into dead ends for no reason with that procedure. All right, and that's a result that we have in the second paper. So I should have not taken, I should not have let it in the conjectures actually. But anyway, well, the conjectures that we don't know. Okay, so that's for the conjectures. Now the results. So it turns out that this model is quite hard to study in full generality on all graphs or even on ZD or Z2. So what we did is that we studied it on some class of graphs called the series parallel graph. Okay, so I'm going to tell you what are series parallel, and then I'm going to tell you what is the result, which is essentially proving the conjecture for the loop erased random walk, loop erased end process. All right, so maybe probably you don't know what series parallel graphs. So if you are into combinatorics, then maybe you know about it, but I didn't know about it before working on that. So how do you construct any series parallel graph? Well, it's constructed in a recursive way. Okay, so the definition is recursive. So first you say that a single edge, okay, N and F linked by a single edge is a series parallel graph. All right. And then you go by induction. So if you have two series parallel graphs, G1 and G2 here, then you can create a third series parallel graph by gluing these guys in series. All right. So you glue F1 and N2 together, and you obtain this new graph here with a new nest and a new source of food, and that's a series parallel graph. Okay. Or alternatively, with the same two series parallel graphs, you can build another third one, which is obtained by gluing them in parallel, right? So you glue the nests together and you glue the source of foods together. All right. So hence the name series parallel, right? Every time you have two series parallel graphs, you can do a third one by putting them either in series or in parallel. Okay, and here I just drew an example of how it looks like. Okay, so it's a loopy, right? You have loops all over the place, but it has some nice structure, and it's not a tree, but somehow there's some kind of similar flavor, right? And what was very useful for us is this recursive definition. Okay, we took advantage of that a lot. All right, so the result that we have on the series parallel graphs is that well, the loop erased end process on any series parallel graph, okay, fix any series parallel graph, then the loop erased end process will find all the geodesics. Okay, so Wn of E divided by N will converge with chi E, where chi E is non-zero if and only if E is on a geodesic. Right. So in particular, if you have something very simple like N is here, F is here, and you have two paths, here it's length L, here it's length capital L larger than L, then the only path that will survive asymptotically is this guy, right? Which is what we want. Okay, but here it's on a simple example. On more complicated example, it's less clear. But at the end, the answer is that you kill the paths that are longer than geodesics. All right, you could still have overlaps, right? So you could have like another path going like that. So the ant in theory could do something like that, but still it survives because it's along geodesics. All right, and yeah, and this procedure finds all the geodesics on series paragraphs. Okay, so the next natural question would be, well, what happens on graphs that are not series parallel, right? That's what you want to know. Okay, so as I said, we don't have an answer to that. It's not a general answer. It's too hard for us for the moment. But we studied a few simple examples, right? And even on these simple examples, actually the proofs to these results are not simple, right? So we use stochastic approximation, and we have to do quite precise estimates, and I mean, it was surprisingly difficult to obtain these results, even on a small graph like that. So the graph we look at here is almost a series parallel, right? It has these two edges like that, but we add a bridge here, which makes it that this graph is not a series parallel. Okay, this bridge losange. And okay, what we prove that the weights on all the edges converge almost surely, that the weight of this edge in the middle dies out, all right, and that the weights of the edge on the outside survive. Okay, so they are both away from 0 and 1, 0 and 1, right? Not 0, not 1. So at the end, we prove that okay, on graphs that are not series parallel, you can still have the result. It looks like we have the result, right? And we did this proof for the uniform geodesic end process. So we believe it's also true for the loop erased one, but again, because we need so precise estimate, actually we couldn't do it in the loop erased case. Okay, we could do it only in the uniform geodesic case. So just to point out that it's you really need fine estimates. All right. And yeah, okay, maybe I should have not mentioned this result, but anyway, the second result tells you that for the uniform geodesic end process, if you have two paths here that have the same length, okay, so you have two possible geodesics, okay, then there is a positive probability that one of them dies out. All right, so that motivates the conjecture where I told you the uniform geodesic end process does not find all the geodesics. Okay, everything it finds are geodesics, but not all of them. Okay, so here it's a proof that not all of them survive in the long term, right? Okay. So I have still 8 minutes. So good. So
Manuel, may I ask you a question?
Yeah.
When you say that not all the geodesics edges survive, it depends on the realization, or there are some edges that like that.
I don't know. I don't know. It could be that there is a phase where both survive, even in this example, right? So what we can prove that there are two events of positive probability, one where this one dies out and another one where this one dies out. And I think that there is a third event of positive probability where both survive, but
But it's not something that has to do with the structure of the graph. It's something that has to do with the randomness of the ants.
Yeah. Yes. Yeah,
Thanks.
yeah. So I mean, and the structure of the graph too, because I mean,
No,
it
of course,
depends on
but
it. Yeah.
let's say there's not such a case in which there is one edge for which for every realization you get 0 there.
Where for each realization, what?
That you get with you always there's, for example, you get two geodesics, but one is never chosen, and you get always 0 there.
Oh, well, not
like different kind of geodesics, let's say. There's not such a
no,
thing.
I don't think so. It's fair. It should be fairly symmetric. Like here, it's clearly symmetric, right? But even if you add, for example, longer stuff here, right? I don't think it would damage too much the symmetry to add something longer from there to there, for example. And yeah, no, I think really what matters is the length of the most used path in any subgraph of your graph, essentially. So even if you have something longer here, this longer stuff will die out quite quickly, actually, and you will only see the shortest path after a while. Okay, if you restrict yourself to this subgraph. So even if you mess around with the symmetry a little bit, shouldn't be that bad. But yeah, no, I don't think it's because of a feature of the graph in that sense. No. Yeah.
Thanks.
All right. So 5 minutes, I can talk to you about the idea of the okay, yeah, for the trace reinforcement process, I'm going to go too quickly on that. Just for the trace reinforcement process, the behavior is very different. And actually, we just proved on a few examples, okay, that this procedure doesn't work. Okay, you don't see only geodesics, right? For example, on this bridge losange, you can see that asymptotically the weight of that edge is 1/2. Okay, so you don't keep only geodesics, right? This edge is along no geodesics, and still it survives, right? So it means that the ants do long ways like that. And same thing here, you have two paths of different lengths. You can assume P larger than Q, for example, but both will survive. Okay, so even on this very simple one here, you don't only keep the shortest path, you keep both paths. All right, and on this example, it's even more ridiculous because you keep a dead end. Okay, so this edge will die out, but you will keep a dead end like that. That will be your asymptotic graph. So really, this process is not a good one to find geodesics. All right, which and it's a pity in some sense because that's the first one you would think of. All right, okay. 4 minutes to tell you what's the idea of the proof. So I'm just going to tell you the basic mechanism. Okay, the proof is I think too technical for 4 minutes, but the basic mechanism is that of embedded polar urns. So let me tell you what I mean. So let's look at this very simple graph. Okay, so here I just put two sources of foods, but you can think of it as only one, right? I just split it in two. So you have one edge on the left, one edge on the right, and that's your graph, right? So at every round, you choose one edge at random, and your end is going to go through that edge from N to F, right? So if the weight is well, the weights are Wn at time n, so the probability to go through the edge on the left at time n plus 1, okay, so to reinforce the edge on the left, is proportional to the number of times an ant has gone through that edge divided by the current time. All right, so the number of ants that were launched up to now. Okay, and it's 1 minus the probability to go through the right. So that's precisely a polar urn, right? Where my red balls is the number of ants that went through the left, and my green balls are the number of ants that went to the right. And that's precisely a polar urn here. And for a polar urn, we know, okay, that this pair of proportions converge to U, 1 minus U, almost surely, where U is a uniform random variable. Okay, So that example is very easy, but it's somehow, I hope, enlightening. Okay, so the idea is that your ends somehow follow the dynamic of polar urns. But okay, the thing is that on the marginal graph, the polar urns are more complicated, right? They are on the top of each other and so on. So let me just point to you why only the shortest path would survive if you believe in this embedded polar urn stuff, even on more complicated graphs. So that's because of the following. So now take the same simple graph, but now the path on the right has length 2, right? You have 2 edges in series. Okay, so now for this graph, if you do any of the procedure loop erase or uniform geodesic, you have the following properties. So the weight of 2 is equal to the weight of 3, because every time an end goes through 2, it has to go through 3, and vice versa. And the weight of 1 plus the weight of 3 is equal to n plus 2, which is the current time or the total number of ends that you have launched. Okay, because each end either go through here or through here, right? So the probability here to reinforce the path on the left is equal again to W1 of n divided by W1 of n plus a half of Wn of 3. And this half comes from the fact that I have length 2 here. Okay, so it's a simple computation about effective resistances. You can just believe me if you don't know how to do it. Okay, you have a half coming up here because it's of length 2 here. Okay, so if you think in terms of polar urn, now it means that every time I choose a red ball here, I'm adding 1 ball to my urn, 1 red ball. And every time I choose a green ball here, I add only a half a green ball, right? Because of this half here. Okay, so it's a polar urn, but where the rules are asymmetric and unfair for the green balls. All right, and in that case, actually, it's also very well known. The proportion of red balls goes to 1 and the proportion of green balls goes to 0. Okay, hence on our picture, only the left path survive. Okay, and the longer path dies out. Okay, so that explains the dynamic of why this process can find shortest paths. Okay, so now when you have more complicated graphs, you have all these paths that are on the top of each other that are intertwined, and so the weights are interacting. So it's more complicated, but the basic mechanism really looks to be explained by that phenomenon. All right, and I'm going to stop here. Thank you.